Good afternoon, everyone. We finally hit 2 o'clock, so let's get started. First off, I have 2 questions for the room. Who has never built a cloud-native application before? Okay, so a good chunk of you have some experience. Secondly, how many of you would say that you're an intermediate developer or more experienced in general? Okay, so we see a pretty common theme here. Most of you have a lot of experience, but building cloud stuff is still something new. So how many people think they're going to have a question just so they know how to paste things? Nobody thinks they're going to have questions. Okay. So I work for Checkfront. Checkfront is an online booking platform for small businesses to enterprise. We deal with inventory management and let our clients' customers self-checkout items. I do a lot of things at Checkfront. I am the lead DevOps engineer, which means that I do a lot of ops and a lot of devs, and no one quite knows what that is. So I used to be the sole operator. These days, I'm more of a developer. In particular, I'm in charge of our cloud operations, be that managing our cloud systems and actually retrofitting old systems or building new systems to be cloud native rather than being a swarm of horrible VMs. So in this talk, we're going to look at 3 main aspects of how to do cloud stuff. We're going to look at what a cloud-native app is. We're going to look at what a cloud platform is and what the implications for our apps are. And then we're going to get to the meat of the talk, which is how do we actually develop for a cloud platform and develop for that behavior. If you have a particular question about the thing that's actively being talked about, just raise your hand. Otherwise, we'll take more general what if or suppose questions at the end. So firstly, what makes software cloud native? It's a very open topic. Cloud Native Computing Foundation is arguably the authority on the subject, and they have a particular definition that software has to be containerized, dynamically orchestrated, and microservice-oriented. Now, number 2 is the part that we should really be caring about, because this is where the requirements come from. If we have dynamic orchestration, this means that we have ephemeral systems, we have things being scheduled up and down as need be. So because of that, it naturally leads to containerization in some form, be that actual containers, be that application images, because we need a system that we can easily ship out in units rather than trying to maintain individual VMs and persistent states. It also means that service-oriented architecture, even if not actual microservices, become very valuable because different systems have different constraints, and we need to be able to handle those separately. Even if it's just a monolithic app and its database, there becomes more separation in that system. As I said, the definition of what is and isn't can arguably be very vague, but there's fundamentally a couple properties that cloud systems have and that legacy systems, or at least non-cloud systems, don't have. So in a cloud system, scaling, load balancing, and replication are all very automated things. You don't have to touch a lot to actually make the system do what you want. And application rollouts are simply as pushing out a new image rather than going in, using Ansible, using Puppet, using manual operations to get things the way you want. That's not the kind of thing that usually should happen. In a non-cloud system, of course, this is your bread and butter. You have a team of sysadmins going in, changing things. You'll have some machines that are broken because someone did something wrong. And you won't be able to easily change your fleet, especially if you don't have some kind of scaling available at the database level. So what's a cloud platform? The first thing is that a cloud platform is absolutely necessary for any cloud system. Ultimately, it's part of the definition. There has to be something that's doing this managing. Your cloud platform can be Kubernetes. It could be something more specific like Rancher. It could be hundreds of lines of horrible bash scripts that somebody at your company wrote. The point being, it's the management system. It's responsible for dealing with the actual infrastructure, so allocation, tear down, and spin up of the resources, such as VMs, disks. It's responsible for actually pushing the applications out, so going from some kind of an image to turning that into actual instances. And it's responsible for handling the network. First thing that the platform does is it is the runtime environment, somewhat analogous to the scripting engine of a scripting language. So it handles the actual physical platform things. It handles the container runtime. If you have a Docker image, you can't run it without Docker or without some kind of container management system. So that's a part of the responsibility. It handles config and secret injection at runtime, and it handles scaling and the networking. So we'll get back to this later, but it's important to note that no matter what we try to do, we can't fully ever decouple applications from the platform. There's always going to be some kind of linkage there. So another thing it does is ephemeral replication. This is why we really like cloud platforms, because resources are just spun up and down as need be. This also really bites us, and it's why data is so scary, because we're used to data having a very constant silo that never changes and never disappears, whereas things changing and disappearing is the absolute backbone of any kind of cloud system. You're specifically engineering against that if you want to handle persistent data. As part of handling the network, a cloud platform is responsible for translating an actual request for an abstract service into concretely going to a specific instance. So this behavior is usually fairly abstract. It can be very proactive specific. There's lots of ways to change the behavior, such as things like Flannel or Istio, that are specifically modifying how that works. Usually, your application doesn't have to deal with that logic itself, but sometimes it does. For example, ingresses, they're usually fairly specific and limited. If you want to have very specific features, such as one instance that I personally had trouble with is custom runtime TLS certificates from white-labeled websites on a load balancer. That's pretty difficult because load balancers and ingresses are specifically built in certain ways in a lot of platforms. It doesn't make them amenable to easy changes or modifications. Okay, so now we know a little bit about what the platform is and kind of what we're working with. So how do we actually develop for it? So in this talk, because it's aimed at people who have at least a moderate amount of skill with developing, we're going to try to focus on what makes this different from developing for more traditional systems. Essentially, if you took your knowledge from 10 years ago, what would be broken or bad or slow in a cloud environment? So there's a lot of things that we could focus on. I'm going to try to focus on high concept here because we're short on time. So in particular, I've kind of plucked out persistent data storage, service coupling, internal API calls and data flow, and then how we handle testing and local development. First up, with persistent data storage, I've identified 4 fundamental patterns for replication. We can have only one replica. We can shard our data without replication. I call this unreplicated shards. So it's just when you have multiple distinct databases, none of them are replicated, but you can have specific things on a specific database. You can have multiple replicas with volatile data that's session specific, or you can have multiple replicas with runtime replication. We'll look at each one of these in a bit more detail and how you use it. First one is just don't replicate. You usually don't want this. If it goes down, it's lost. If it's getting swapped out with an upgrade, it's offline for a couple seconds. You might want this for services where the impact is fairly low. For example, we have a fairly small company, and the people who handle ops are one dedicated person and me a little bit. So we don't cluster our Redis setup, which we use for a couple things. In particular, one thing where Redis isn't clustered is for our translation master, for being able to translate our internal English strings into customers' multi-language strings. We don't cluster it because the impact is if that one instance goes offline, people can't save new global translations. It doesn't stop the basic functionality from working. So that's an okay trade-off for us just based on operational concerns. Next pattern is unreplicated shards. This is a pretty common strategy, both for kind of manual load balancing and when you naturally outgrow the ability to have everything in one database. It's when you pick some kind of unit, typically an account, and you specifically put it on a certain system. Usually it's like US West 1, US East 1, things like that. So it lets you scale up your system as a whole, but the individual components aren't actually scaling. You still have a database where if it goes down or gets overloaded, it's just not working. Third strategy is having multiple volatile copies. It's really easy to do by accident, and I've seen a lot of bugs that wind up being something is stored on disk as if it's persistent, but there's multiple instances. It's a good pattern for caching, but I would highly recommend ever planning on using it, just because there's always going to be circumstances where the data becomes ephemeral when you don't expect it. The last strategy is what we always really want. We want to be able to just have a bunch of databases, everything works together, we hit a database, we read and write to it, and we don't have to worry about having only one. This is the goal, but it's really hard, especially for the operations side. So this is one of the first things where you really have to deal with the operations and dev planning to actually make sure that what you want to do is feasible to actually run. So some databases are very good at this. Cassandra is one I've worked with a fair bit. So Cassandra is naturally multi-master. It has a lot of quirks, but one of the things it's best at is you just have a lot of instances and you don't have to worry about many of the concerns around scaling. If you take something that doesn't scale very well, Postgres can be an example of this. We use Postgres a lot. It scales nicely for read replicas, but the masters are something you primarily deal with election for. So this means you have to handle election of a single master, deal with kind of playing hot potato there, and if you have too many writes or too much load for the master, then tough luck. Usually, unfortunately, databases are not, as you all know, something that you can just easily swap out. So you need to kind of understand what your runtime load's going to be, what your needs around latency and replication are going to be, and pick a database based on that. So if you're trying to run something like Postgres and you just have too much writing going on, you're going to have to look at sharding it, or you're going to have to look at changing the way you store data and adopting something else like Cassandra or like Mongo or another document-oriented system that lets you actually replicate at the scale you need to. As I kind of outlined a bit in the last slide, replicating data is pretty tough. There's just a lot of concerns around it, and databases that are more friendly towards replication tend to handle more of this internally, whereas ones that are less friendly tend to outsource a lot of that to kind of custom scripting, custom tooling, and manual operations. You have to deal with allocating persistent volumes, binding to those, connecting to either seed nodes or masters, and dealing with electing and maintaining those. Ultimately, especially if you're a small team, third-party tools can be really handy for this. So GCS or S3 for images is a really good example. You are almost always okay with just serving images from a CDN in most use cases, and suddenly you don't have to worry about replicating all your images locally. Our next topic of what's difficult is service coupling. So there's kind of two parts for services, but first we're just going to look at how services interact together. We want to keep things that are interacting a lot together, close together. So in Kubernetes, which we're probably all most familiar with, deployments naturally are creating a unit called a pod, which contains multiple containers. So there's nothing too complicated there as far as setting that up. What's special about pods is you create containers that are co-located and co-scheduled. So there's one-to-one state between your containers in a pod, and they're always on the same machine. So this is especially useful if you have high latency concerns for your connectivity. We want to couple things that are calling one another a lot, either when it's very, very critical that a call goes through okay, or when overall you're making a lot of back and forth calls. So if you have a particular service that makes many, many calls to the database over the course of a single operation, you're probably going to want to be able to put those things in a pod together so that you're just going over the local network socket as opposed to hopping to the next rack or the next data center. It's also good if you have any kind of system that relies on particular state between services. Rather than dealing with nasty pinning at the network layer, you can just inherently know that a particular instance is going to talk to another particular instance always. Here's a quick example of using the shared state to our advantage. It's a pattern that's often used when there's frequent content changes or content changes that aren't part of the source code. You can simply have a web server and a shared disk with a file pulling image that is taking data from an external source, pulling it onto the local disk. This way, the Nginx image in our example doesn't have to ever be updated with new content. So we don't have to worry about swapping everything out or putting content into our build system. So service coupling can solve a lot of problems around latency, at least primitive ones, but we can't couple everything together. We have a lot of concerns around replication of some services, in particular ones with persistent data. As we kind of talked about, there's a lot of issues around dealing with the resources, the spin up, the replication, loading things. If we try to pin a stateless service along with the database, we're going to find that the stateless service is hard to schedule and it's hard to spin up because it's limited by what the database can do. We're also going to have trouble with allocating resources. Unfortunately, putting resources in a pod means that you're specifying per container what the resource allocations are going to be. So suddenly you might wind up needing 12 units of CPU to schedule your pseudo-monolithic application, when really you're trying to just scale up the reporting system. And because you can't scale selectively, you are going to over-allocate stuff, as well as having trouble just finding a big enough resource block to put an entire replication of the pod. So this starts getting into monolith territory as far as your runtime concerns. Related to services, there's also internal data flow. I called it internal API calls, but it's a much more open subject. It's not just how you locate services together, it's how you actually transfer data between those services. Cloud platforms tend to exaggerate this latency by means of either physically separating things further, such as breaking up a monolith, or by the encouragement to go for a more microservice-oriented design. Something that used to be local network socket or even just a function call away is now a little bit further. That latency is often just nanoseconds to milliseconds, but this can vastly add up depending on your call flow and your architecture. The first thing you can do is use threads or use async. Checkfront works with a lot of PHP, and as those of you who've unfortunately dealt with PHP know, this isn't very possible. But you can get out of a lot of hot water just by parallelizing every single request that you are able to that's independent so that you're not waiting on all these back and forth calls. That said, you can't always do that. Sometimes your language doesn't support it, and sometimes you just wind up in a situation where the fault is an upstream design that you're having to go back and forth with a lot. In that case, you need to go to the upstream. One thing you can do is simplify your API actions. So REST APIs in particular are often guilty of secretly just being database CRUD. This is unfortunate if your data is a little bit too normalized because you'll wind up having to make a bunch of API calls to do one high-level action. So it's very common, I'm sure you've all experienced this, going to an API, querying it, selecting some data, and then inserting that data into your next query, either for updating things or for trying to fetch something. Ideally, the API endpoints can be designed in such a way that you have one discrete action wrapped up in one endpoint, rather than trying to step through multiple pseudo-database calls. You can create batch endpoints. So this allows you to escape a tiny bit of networking overhead, and it allows you to leverage any shared work common to your calls. So doing query planning and pre-processing, initializing data structures, information that you have to fetch before handling requests. If you can make this common, then you can vastly improve your overall response time. This is really useful if you're trying to bulk load something, like say if you have a social media application and you're trying to load a whole bunch of posts. It's really nice to be able to do that in one fetch versus in a single request trying to load 50 different things and making 50 different calls off. I have a quick example for how this can be beneficial with SQL. I'll get to it later just because I can talk about some testing things at the same time. Sorry, I just want to check how I'm doing for time here. Okay. We can easily cache things, especially if we design our services to be stateless such that we don't have to worry about cache expiration. So we can design this for more processing-heavy things at the server side where we have to make the network call, but we don't have to actually worry about reprocessing anything. If we're more worried about network call or just eking every last bit of performance out of it that we can, we're going to want to put it within the client so that the call never has to actually leave the pod or leave the container even. So for testing, this becomes awkward the more components you have. Suddenly, instead of having one thing that you just run, you have a lot of different things that need to run together. You also need to be able to run them whatsoever. Unfortunately, you can wind up in a situation where you have to just install Minikube to get anything done. As those of you who've done this will know, it's not very friendly for developer workflow. You can't iterate quickly, and you suddenly have to know a lot about the entire application and the operational concerns to just get off the ground. We really don't want that, and if we don't want to be forced to do that, we have to design it a little bit with our testing and development concerns in mind. Ultimately, what you want to be able to do is create discrete components of the application that can be run individually, either just as trees of services that call one another, or with fake endpoints that aren't necessary for your purposes. So if you're testing, chances are you can only run a service or two and just mock up things it interacts with. You don't have to worry about everything that it's going to call. But to do this, we need to organize our call flow in such a way that we don't have an absurd number of dependencies for a given action. Here's a quick example that will probably be fairly easy to understand as far as unit testing goes. So for unit testing, we want to be able to simplify our actions as much as possible. And ultimately, here we have some business logic, which is just statistics.median that we want to be able to test in detail. And we care less about detailed testing of the overall function. The awkward way to do it is to have one function that does everything, and suddenly we need to get into the database to write values, call the function, and then read them out to do our test. This is really awkward, especially because the bulk of what we're trying to test in detail has nothing to do with the database. The nicer way to do it is to specifically split the logic out into its own function, and that way we can call that function without worrying about the database at all to test the business logic, and then do a simple test or two for does the whole database process work. In terms of services, we have a diagram here that kind of represents the same architecture. We have our database, an interface for it, reporting API, and a reporting backend. The reporting backend represents that statistics.median call in the actual code example. This is something that, in this architecture, doesn't depend on anything. It doesn't depend on a database integration because it's having data dumped into it in individual calls. So you can test that backend without the database at all. And you can also split off different portions of the architecture as need be. You could test the reporting API using static payloads, even just HTML pages, on the inventory fetch API and the reporting backend. So suddenly we've vastly simplified our concerns for what we need to run to either test or develop for a particular service. Local development has a lot of the same concerns as testing does. We need to have a limited number of things we need to run. It needs to be easy to run them, and we need to be able to get the service that we're focusing on up quickly. One thing that's very nice for this, especially if you can develop small enough services that running them is just install the package manager, run the application, is you can actually not use Docker. This has been talked about at a number of talks so far this week. Developing with Docker or a container runtime is not very friendly. If you have that make a change, build, run cycle, that's a lot more awkward than the change a line, hit the button in the IDE flow. So one design that we do at Checkfront is, especially with more service-oriented architecture that we're exploring, we try to have a Docker compose file that deals with all the necessary dependencies of a service for testing or development, and then natively run the actual thing that we're developing on. This way we don't have to worry about the build cycle at all for a particular component. And this just means that we have a special development/testing Docker compose file for each service. Okay, I've been through a lot of content. So the key takeaways should be that many things wind up being platform specific. And this involves ultimately a lot of knowledge around operations around the platform. So you should be actively working with the people who are going to be building and maintaining your cluster, ideally before you even lock into specific services or clusters or behaviors as to what you need and how you're going to get it. What you really don't want is to wind up with kind of the dev to ops pipeline that a lot of companies have, where something gets built, it gets thrown at the ops team, and it's kind of, well, just run it, figure it out, because that doesn't really work. You wind up with things that can't scale, or you wind up with things that just aren't going to be performant in ways that could have been predictable and negotiated in the design phases. And service architecture winds up being kind of the be-all and end-all of this. We have to split up our services due to different runtime concerns around load and around data storage. And even if we don't go the full microservices route, we need to care a lot about how we couple these things and how they interact together. So I'm going to go to the quick demo now for doing batch calls with SQL. It's only a couple lines of actual logic, but I want to kind of prove that that's something that's more performant. So I'll open up the IDE with the actual logic here. And I'm also going to boot Docker. Okay, so we have a pretty simple tool that just is connecting to a database, making it query, and doing a little bit of clever/hacky SQL for dynamically inserting something in the where clause. So we can select multiple people in this. I don't know how to scale this up, but trust me, it's only like 3 lines of logic. So first we're going to go Docker Compose up. We're going to start Postgres. We're going to set the Postgres password with an environment variable so that it's not hard-coded. Everything else is using defaults, but we don't want to actually have to put that in the source code itself, even for a demo. Although the password is demo, so. Okay, populate the database. Now, so if I call it with making just one query, it's only querying for one ID, I get 0.014 milliseconds. And if I query again, it's bouncing between about 0.1 and that. So I have a pre-prepped line that's just making a lot of queries to different IDs. It's just making the one call of main.py, but it's throwing in, I think, 40 different IDs that it's looking for. But because this is only one query, we're still seeing it in the same time range. It's still showing up between 0.01 and 0.015 milliseconds. So if we were to stack that up, that could become very substantial very quickly if we were to make all those calls synchronously. But because we're making one query, we're taking advantage of the fact that the query planner is already running and we're already scanning through the data. There's a tiny bit of, obviously, overhead for more data that you're selecting, but it's almost trivial in comparison to just making the call that many times. I'm sorry, I appear to have lost my slides. Okay, so I have a few pieces of suggested reading here. Personally, although there's no substitute for experience, I find it very helpful to have tutorials and have books and have high-level overviews that deliver a lot of the concepts to you so that you actually know where to be exploring yourself. In particular, I'd probably recommend Designing Distributed Systems, which I read only a couple weeks ago, but it outlines a lot of kind of the basic patterns in cloud systems, kind of like container-level patterns for what you traditionally have as object-oriented patterns. Okay, so I'm guessing that a few of you probably have questions about this kind of stuff. So there's a microphone up here, or if you shout something out, I can repeat it.
Thank you for your talk. And at this conference, I've heard of some people who are starting to do development also on systems that are running in the cloud and on the cloud servers. So have you experimented with having, instead of having the IDE run it locally, which is what we do as well, so having instead run the code, modify the code on the containers as it's running, and then testing, like developing on that?
So the pattern of specifically sharing a volume, you mean? Do you mean the pattern of sharing a volume with the container and using that locally?
Well, having a kind of file puller that pulls from your IDE or is like syncs with your IDE and then actually runs that code in.
Right. That pattern can be helpful, but it depends exactly on what you're working with. Sometimes it can be awkward, especially in terms of package management, to deal with that kind of shared state. And I found there's a bit of a false positive that can happen where you have the correct state locally, but you're trusting so much that the built container works fine that you then have something that works on your machine, you deploy it, you go, I was using the container image, and then it fails on Jenkins.
Okay, thank you.
I can just shout. How much of your time do you spend on tooling for developers?
Nowadays, not much. I officially started as a sysadmin, but I've always been more development-oriented, so I would say that maybe good quarter to a third of my time used to be spent on that, but these days we buy more tools or use more mature platforms like Kubernetes over in-house VM management. Anybody else? Thank you.
I'm totally with you on the part where you can locally develop without Kubernetes or Minikube, but how would you handle service discovery in that case? If you need, I mean, if you're developing on maybe 2 services, which is reality in a microservice world where in a perfect world you would only need to work on one, but they do need to talk to each other and they need to discover each other. How would you handle that?
The practice that I've found best for that is specifically spinning up a compose environment or some kind of bash launcher for your containers and having basically config level routing, maybe with defaults for production, but always having the ability to inject the host and the port and so on for whatever you're actually trying to connect to. So this is perfectly fine if you've got a handful of services. Maybe if you have 30 services that a thing is trying to connect to, this would be ugly to manage, but at that point, you have one service connecting to 30, you're starting to have other issues.
So you're running your developing services where you're doing a feature in containers. You're not running them totally from your IDE, like Python, Java, whatever you're doing.
No, the point of trying to run locally just is that it's a little bit nicer for the thing you're actively working on. But for the other dependent services, you may as well just throw them in a container. It's easiest. It's not that I have something against containers. It's simply that it's a little bit nastier to try to develop in one on the thing that you're actively working on. Other components, it's nice and quick.
Thanks.
Sorry, I'm getting a little bit of light glare. Anybody else have a question? Okay, I guess I'll wrap it up there. If you have any other questions, feel free to approach me personally or send me a message later. I'm planning on trying to start some kind of series around development concerns for modern architecture and cloud stuff. I'm not sure if it's going to be office hours or a blog or whatever. Really depends on what kind of interest there is. Thank you all for joining.